Suppose you have a sheet of aluminum foil, and we'll just make it 1 meter by ½ meter. And I want to make a capacitor out of it. If I cut it in half, then I basically can have two sheets here, ½ meter by ½ meter. I can stick some dielectric in between. And I create a capacitor. So basically I'm taking the sheet, cutting it in half, and then put a dielectric in between it. I create a capacitor. So my capacitance would be kappa epsilon naught A over D, where the area is 0.25. So there'd be 0.25 times the dielectric constant of whatever I stick in the middle times this constant here divided by the thickness. The question is, with the same sheet of aluminum foil, could I get something of greater capacitance? So we assume that we have a constant dielectric of a particular thickness, and so this is just some constant. So I'm going to take this sheet and I'm going to break it up in, I'm going to take 1/3 off of it. So let's actually go to a new sheet. So I take my piece of aluminum foil, and that's ½ meter by 1 meter. I'm now going to cut this and take 1/3 of it off. So this is 1/3 of a meter, and this is 2/3 of a meter. I will now take my 2/3 of a meter and fold it. So basically I have 2/3 of a meter here. I fold it up. So I have it folded like that, not drawn to scale. 1/3 of a meter, 1/3 of a meter. That's this piece right here. And I take my other 1/3, the one that I cut off, and I stick it in the middle. Kind of like a sandwich. And then I stick my dielectric in here, the lettuce of capacitors. I've got some charge here, so if I hook this into a power supply, I have a negative charge on this right here, and then I'll have a positive charge here and a positive charge here. That's actually a little bit misleading. I'll have -2Q. Let's look at it in a slightly more familiar form. I've got some charge on the outer one, Q, here, and I'll have the same charge on this one right here. There's no reason why these charges would be any different. In the middle, I have a piece that, this is the 1/3 right here. I'll have -Q on this side and -Q on that side. It's like I've got two capacitors here, where this is hooked to the negative side of a battery, and then the positive side is hooked to those. Drawing in a slightly different form, I have my Q right here. I have a -Q there. That is hooked to another side, which also is -Q, and I have Q here. I'll have this hooked to the negative side of the battery, and my positive side of the battery will be hooked there. Putting in a slightly different form, I have my battery. The negative side is hooked to two negatives right there, so it's going to come up and split. So I've got a negative side there and a negative side there. Each of those has a corresponding positive side, so there's my -Q, -Q, Q, and Q. And the positive sides are connected to that. In essence, what I've set up here is two capacitors in parallel. So the size is cut in, well, basically it was 1/2 by 1/2. Well, now it is 1/2 by 1/3 meters. And so my capacitance of this one right here, we'll call it C1, is kappa, so the dielectric constant for the dielectric, times epsilon sub naught, permittivity of free space, times my area, which is 1/6, divided by the distance between them. The distance is still the thickness of the dielectric. I have two of them in parallel, so that's also equal to C2. And so my equivalent capacitance is twice that, or 1/3 kappa epsilon sub naught over D. So by taking my piece of aluminum foil here with a little bit of thought, I actually can create higher capacitance. This was 1/4, this is 1/3. Now the question is, theoretically, assuming we don't have to worry about the thickness here of the aluminum foil or the dielectric. That's a slightly different problem. The question is, what is the largest capacitance you could get out of a 1 by 1/2 sheet of aluminum foil? And that might end up being a test question someday.